Right now, as you are reading this, there are people in the exact same room conditions as you, sweating through a heat wave, and they have no idea that a $5 solution is already sitting somewhere in their house waiting to be used. There are at least 6 distinct methods covered in the next few minutes of this video, some of them thousands of years old, one of them rediscovered by a university lab just a few years ago, and one of them so embarrassingly simple that once you know it, you'll be genuinely frustrated that no one told you sooner. Do not skip any minute of it, because the one that will matter most for your specific situation is probably not the first one, it might be the last one, and every single method here is chained into the next one in a way that makes the combined effect dramatically more powerful than any single trick alone. In 2026, electricity costs have surged across dozens of countries, fuel supply chains remain disrupted from ongoing conflict in the Middle East, and grid instability has become a routine reality in regions that used to take reliable power completely for granted. Air conditioning, which was already the single largest consumer of household electricity in hot climates, has now become a financial pressure point for millions of ordinary families who simply cannot afford to run it the way they used to. Here are 6 real, scientifically documented cooling methods, explain exactly how each one works at the physics level, show you how to build or apply each one, and then reveal something that almost no one talks about, which is the way these methods interact with each other to create a cooling effect that is far greater than the sum of their parts. The first method is the one most people have heard of, but almost nobody uses correctly. And getting it wrong actually makes your room hotter, which is why we are starting here. It is called evaporative cooling, and it is the most powerful passive cooling force in nature. The same mechanism your body uses when it sweats, the same mechanism that makes a breeze feel cold on wet skin, and the same mechanism that ancient civilizations used to keep food cold in the desert thousands of years before refrigerators existed. Before refrigerants existed, evaporation did the same job, and when water evaporates, it pulls heat from whatever surface it is leaving. The principle underlying evaporative cooling is the fact that water must have heat applied to it in order to change from a liquid to a vapor, and when evaporation occurs, this heat is taken from the water that remains in the liquid state, resulting in a cooler liquid. This is not a trick or a metaphor. It is a fundamental thermodynamic law, and it means that whenever water transitions from liquid to vapor anywhere near you, it is physically stealing heat energy from the surrounding air and carrying it away. When you blow hot, dry air over water, the water evaporates and takes the heat energy from the air to do so, and as a result, the air gets cooler. The simplest and most immediate application of this principle costs you nothing. If you already have a fan, a bowl, some water, and a cloth, and it works like this, using nothing more than a frozen water bottle, a damp cloth, and a fan, you can create a makeshift air conditioner that actually works. The science is straightforward. As frozen water melts and evaporates, it absorbs heat from the surrounding air, while the fan circulates this cooled air throughout the room. The damp cloth creates additional evaporative cooling as water evaporates from its surface, and the positioning matters too, as placing the setup directly in front of the fan ensures maximum air circulation across the cold surfaces, creating a localized cooling zone that can drop the temperature by several degrees, making small spaces noticeably more comfortable. But here is where most people get it wrong and actually make things worse rather than better. The process called the latent heat of fusion requires significant energy, about 80 calories per gram of ice melted. This means the ice is doing serious thermodynamic work and absorbing a measurable quantity of real heat from the air around it. But the moment that ice bottle is sitting in a warm, open room without a fan, directing that cooled air anywhere, the cold dissipates in seconds and the effect is wasted entirely. Forced convection, meaning the fan creating airflow over the cold surface, is what accelerates heat transfer and pushes the cooled air toward you, because without the fan, you would just have a bucket of melting ice. You also need to fill your bottle correctly before freezing it. Fill your chosen bottle with water to about 75% capacity, leaving room for expansion as it freezes, because this is crucial since overfilled bottles can crack or become impossible to stand upright once frozen. If you have freezer space, consider preparing multiple bottles so you can swap them out for continuous cooling throughout the day. For maximum effectiveness, close windows and doors to contain the cooled air in your target space, because this works best in smaller rooms like bedrooms or home offices rather than large open areas. Now, while the frozen bottle setup is the fastest way to feel immediate relief, the next variation of this method is something built from almost nothing, and it lasts longer, produces more consistent cooling, and has been validated by multiple engineering studies. It is called a swamp cooler, more formally known as an evaporative cooler, and it has been used in dry, hot climates for decades before modern air conditioning became the standard. A swamp cooler, known more formally as an evaporation cooler, is the ultimate in low-tech cooling system, cheap to make, and relying on the fact that heat is needed to turn water into vapor, and that heat is taken from the air to do it. Swamp coolers work on the simple but effective method of evaporative cooling, meaning they require a minimum of 3 things to function properly: water, dry, warm, or hot air, and purposefully directed airflow. To build the most effective version at home, here is exactly what you do and why each step matters. Most DIY swamp coolers consist of a 5-gallon bucket or similar sized container with a lid and 2 holes, where one hole is for the intake of fresh, warm, or hot air through the lid. And the second hole, more likely a series of holes, is for blowing the cooled down air back out through the sides. You then cover those holes with cloth, securing the cloth on the inside of the bucket so that part of it reaches the bottom of the bucket, which allows the cloth to soak up cold water, and the fan will pass air through the cold, wet cloth, which creates the cooling effect. Add cold water and ice to the bucket, filling it just below the holes in the side. Refill with cold water and ice as needed. And alternatively, a frozen gallon jug of water can be placed inside the bucket, which makes cleanup and refilling easier. A well-built version can drop the temperature in a 90 square foot room by a full 10 degrees. But here is the critical caveat that no one tells you up front, and that will save you from wasting your time and frustration. Swamp coolers work best in dry climates and indoors. The one word that matters here is dry, because in low humidity environments such as the Southwest, high desert, and inland areas this works extremely well. But in Florida in August, wet cloth in a window adds misery, and you need to know your climate before you count on this method. In arid and dry climates, evaporative methods, including wet curtains and the Zier pot, are highly effective, but in humid climates, evaporation is limited, and the focus should shift to shading, ventilation during cooler hours, insulation, and preventing heat gain. So if you are in a humid environment, do not give up yet, because the remaining methods work even better for you, and you are going to want to stay for all of them. Now, the science gets even more interesting with the next method, which dates back to ancient Egypt, was reinvented by a Nigerian teacher in the late 1990s, was then studied by engineers at MIT, and is now being tested in Bangladesh and across sub-Saharan Africa as a serious heat adaptation technology. It is called the Zier pot, also known as the pot-in-pot cooler, and it is one of the most elegant passive cooling devices in human history. 2 clay pots, one inside the other, wet sand packed between them, a wet cloth over the top, set in a shaded and breezy spot, is the Zier pot, or the pot-in-pot refrigerator. And as water evaporates through the porous outer pot, it pulls heat out of the inner chamber. The Nigerian teacher developed the modern version of this in the late 1990s, and in dry conditions, he kept tomatoes fresh for 27 days against 2 days in open air, which changed the entire game on food storage without power. A pot-in-pot refrigerator, clay pot cooler, or Zier, which comes from the Arabic language, is an evaporative cooling refrigeration device that does not use electricity. And a Zier is constructed by placing a clay pot within a larger clay pot, with wet sand in between the pots, and a wet cloth on top. Research reviews of pot-in-pot systems show that, on an average, they lower the temperature between 8 and 18 degrees Celsius, increase the relative humidity between 40 and 60%, and such systems are more useful and efficient at places nearer to the equator where there is comparatively hotter ambient temperature with less humidity, while also being economical and cheaper than other refrigeration and space cooling techniques. The engineering of this device was taken seriously enough that MIT's D-Lab conducted formal field trials of clay pot coolers in Mali and Rwanda, tracking temperature, relative humidity, and sand moisture at 5-minute intervals using electronic sensors. Clay pot coolers are low-cost technologies that can prolong vegetable shelf life by providing a cool and humid storage environment through evaporative cooling. Results of the MIT study show that the pot-in-pot devices consume 1.96 liters per day of water, making them extraordinarily resource efficient. Researchers at the Indian Journal of Advanced Research in Engineering, Science and Management also conducted experiments combining an earthen pot with forced convection using a blower. Their setup showed that the water temperature can be reduced by up to 7 to 8 degrees Celsius, and air can be cooled by up to 2 to 3 degrees Celsius simultaneously. And the shape of the pot itself turns out to matter more than you would ever guess. Earthenware pitchers with smaller aspect ratios, isolated support bases, and a belly positioned closer to the bottom were found to be more effective in cooling and slower in the evaporation process. Vessels with smaller water volumes tend to exhibit faster cooling due to quicker evaporation, while larger surface areas facilitate improved heat exchange. Now, while the Zier pot and swamp cooler are working their magic in your living space, there is a parallel battle happening above your head that most people have completely surrendered without realizing it, and that battle is the one happening on your roof. On a sunny summer afternoon, a conventional dark roof can reach temperatures of 150 degrees Fahrenheit or more. Conventional roofs can reach temperatures of 150 degrees Fahrenheit or more on a sunny summer afternoon, but under the same conditions, a reflective roof could stay more than 50 degrees Fahrenheit cooler, which can save energy and money in buildings with air conditioning, or improve comfort and safety in buildings without air conditioning by reducing heat flow from the roof into the occupied space. All of that stored heat in your dark roof radiates downward into your ceiling and then into your living space throughout the entire day and into the night, meaning that even after the sun sets, your roof is still pumping heat into your home like a radiator that you paid nothing to install and cannot turn off. The solution is almost embarrassingly low-tech. A cool roof absorbs and transfers less heat from the sun to the building compared with a more conventional roof. And a high solar reflectance, also known as albedo, is the most important characteristic to understand in terms of how well a cool roof reflects heat from the sun away from a building. White roofing products stay coolest in the sun, reflecting about 60 to 90% of sunlight. A cool roof lowers the amount of heat transferred to the building, which allows it to stay cooler and use less energy for air conditioning, and in air-conditioned residential buildings, solar reflectance from a cool roof can reduce peak cooling demand by 11 to 27%. In non-air-conditioned residential buildings, cool roofs can lower maximum indoor temperatures by 1.2 to 3.3 degrees Celsius. Now, studies from real-world application have shown results even more dramatic than laboratory predictions. In Senegal, 2,390 square meters of roofs were painted in white, resulting in a 15 degrees Celsius reduction of roof surface temperature and up to 31 degrees Celsius reduction on the warmest days. Teams who participated in the Million Cool Roofs Challenge measured indoor air temperature reductions of over 10 degrees Celsius in some of the pilots. A study conducted on a roof in Sicily, Italy, showed something even more striking. The numerical and experimental investigations revealed the surface temperature of the roof reduced by up to 20 degrees Celsius during the 24-hour period cycle, and a 54% reduction of the cooling energy demand was achieved using the cool roof. And in Morocco, researchers compared 3 passive roof techniques side by side. The white-painted roof had the highest thermal performance, and it reduced the ceiling temperature by up to 13 degrees Celsius relative to the reference cell, while the measured data proved that the white-painted roof reduced the heat flux by up to 66% through the roof slab. UCLA Materials scientists have gone even further, developing what they call super white paint that reflects as much as 98% of incoming solar radiation. Materials scientists have demonstrated ways to make super white paint that reflects as much as 98% of incoming heat from the sun, and the advance shows practical pathways for designing paints that, if used on rooftops and other parts of a building, could significantly reduce cooling costs beyond what standard white cool roof paints can achieve. The researchers showed that simple modifications in a paint's ingredients could offer a significant jump in reflectance, going from the standard 85% up to as much as 98% of incoming radiation. This does not require special industrial materials for the basic version, however, because simply painting your roof with ordinary white paint is a verified intervention that costs the equivalent of a few meals and produces measurable year-round cooling. Cool roofs are likely the most affordable and simplest of heat management system solutions for vulnerable populations. But what happens if you cannot paint your roof? Maybe you rent your home. Maybe your roof is inaccessible, or maybe you live in an apartment building where the roof belongs to everyone and no one. The same reflective principle can be applied at the window level, and that is the next method in the chain. Your windows are the weakest thermal point in almost any room in terms of solar heat gain, because glass does almost nothing to stop infrared radiation from the sun, and a single south or west-facing window on a sunny afternoon can pour as much heat into a room as a small electric heater running continuously. Blocking the sun using reflective window film, blackout curtains, or even aluminum foil to prevent solar heat gain is one of the most cost-effective immediate interventions available. Using blackout curtains, heavy blankets, cardboard, or reflective emergency foil taped to window frames, as exterior shading is more effective than interior treatments, and a cardboard and foil combination in a simple wooden frame or plywood painted white works extremely well. The physics reason that exterior shading works better than interior shading is important to understand because it changes what you do with your $5. When you hang a blackout curtain on the inside of your window, the sunlight has already passed through the glass, already converted to heat inside your room, and the curtain is now trying to block that radiated heat from spreading further, which is a losing battle. When you place a reflective barrier on the outside of the window or on the outside of the glass, you stop the solar energy before it ever enters the room, meaning the glass never heats up in the first place, and your room stays dramatically cooler. Installing shade cloth, bamboo screens, or simple awnings over windows and walls, along with fast-growing vines or trellis plants, provide evaporative shading and cooling at essentially zero cost if you can grow them. Even a simple piece of cardboard wrapped in aluminum foil and placed in the window frame on the sunny side of your house at midday is doing real thermodynamic work. And studies confirm this is one of the highest return on investment cooling interventions available to anyone regardless of income. Now we are at the part of this video that almost nobody talks about, and this one changes everything if you understand it, because it is the method that transforms your home itself into a cooling machine that works while you sleep. It is called thermal mass and night flushing, and it was the primary cooling strategy used by every culture on Earth before the invention of mechanical refrigeration. Here's the principle. Dense materials like concrete, stone, brick, tile, and even large containers of water absorb heat slowly during the day and release it slowly at night, acting as a thermal buffer that smooths out the temperature swings between day and night. Night ventilation is regarded as a promising cooling strategy by storing night cooling in the thermal mass of the building. Sufficient nighttime natural ventilation can lower indoor temperatures by more than 3 degrees Celsius below the outdoor air temperature. Internal mass with a lightweight wall achieves peak cooling load reduction by 35.9%. The technique is this. During the cooler hours of the night, typically from around 10 p.m. until sunrise, you open every window and door in your home as wide as possible and use fans to actively pull cool outside air through the space. The window fan technique involves placing a box fan in your window at night to pull cool outside air in, and reversing it during hot days to push warm air out. Cross breeze creation involves positioning fans to create airflow paths through your space, where one fan pulls air in and another pushes it out. This moving night air charges the thermal mass in your walls, floors, and furniture with coolness. And then when the hot day arrives, you close everything up tightly before the outside temperature climbs past your indoor temperature. Open windows widely after sunset, close them before sunrise, and seal with towels and curtains to trap the cool air inside. Implementing the night flushing method to cool your home during cooler hours is one of the most proven and studied passive cooling techniques available. The stored coolness in the mass of your building then acts as a heat sink throughout the day, absorbing the heat that enters before the room temperature can rise sharply. Using passive strategies in combination with low-energy strategies that elevate air movement like ceiling or pedestal fans enhances the cooling effect by 3 times compared to using fans alone. And this is where the chain reaction of methods starts to compound in a way that is genuinely extraordinary to think about. If you have sealed your windows with reflective barriers to reduce solar heat gain during the day, and you have painted or covered your roof with a white reflective material to reduce radiant heat transmission, and you are running a swamp cooler or fan and cloth setup inside, and you have charged your thermal mass with cool night air, every single one of these is now working together simultaneously. The roof sends less heat down through the ceiling, the windows let in less solar radiation, the thermal mass absorbs whatever heat does get in, the evaporative setup cools the air that reaches your body, and the night ventilation resets the entire system every evening for free. Now there is one more method in this chain, and it is perhaps the most counterintuitive of all 6, because it requires you to think carefully about what is generating heat inside your room that has nothing at all to do with sunlight. Every electrical device in your home that is on, including incandescent light bulbs, televisions on standby, chargers, ovens, ironing machines, and conventional light fittings, is generating heat that directly adds to your room temperature. Cooking outdoors, avoiding incandescent bulbs, and postponing ironing or laundry drying indoors during hot spells, as well as using LED lighting sparingly or relying on daylight, are all legitimate and measurable indoor temperature interventions. An incandescent bulb converts only about 5% of the electricity it consumes into visible light, and the remaining 95% becomes heat, meaning a room lit by 6 incandescent bulbs is also being heated by the equivalent of a small electric heater that is running full time at your expense. Switching every bulb in a room to LED immediately eliminates that heat source, and doing so costs at most a few dollars per bulb, often less, and pays for itself in both electricity savings and temperature reduction within weeks. Now, let us take a moment to connect everything into the full picture of what you are actually building here, because this is the hidden power of this entire approach that goes beyond any single trick. Passive cooling combines shading, ventilation, thermal mass, evaporative effects, and cheap materials to cut indoor temperature without electricity. And practical options range from quick DIY fixes to low-cost semi-permanent improvements. What this means in practice is that each of these methods removes a different layer of the heat problem. And when you stack them, you're not adding the effects, you're multiplying them. The reflective roof coating removes the largest single source of radiant heat entering through the ceiling, which, according to U.S. Environmental Protection Agency data, can represent an enormous fraction of the total heat load in a non-insulated home. The window shading removes the next largest source of direct solar heat gain, which is particularly critical on west-facing windows during the late afternoon when the sun is at its most intense angle. The night flushing and thermal mass strategy uses the natural temperature differential between night and day to reset your indoor baseline temperature. So the room you wake up in is already several degrees cooler than it would have been without any intervention at all. The evaporative setup, whether a simple damp cloth on a fan, a bucket swamp cooler, or even a Zier pot in the corner of the room, removes heat directly from the air you breathe and creates a localized comfort zone around your body. And the elimination of internal heat sources from bulbs, cooking appliances, and electronics means that the rate at which your room heats up during the day is dramatically slowed, giving all your other interventions more time to work. An evaporative cooler will reduce the interior temperature by about 15 degrees Fahrenheit, which is 8 degrees Celsius, compared to the ambient air temperature. And even this level of reduction helps inhibit the populations of fast-growing bacteria that can spoil food quickly. Now let us talk about how the ancient world and the modern engineering world have arrived at the exact same conclusions from completely different directions, because this is where the story becomes something more than just a list of practical tips. The inhabitants of ancient Persia, modern-day Iran, were building structures called yakchal more than 2,400 years ago that used a combination of thick mud brick walls, which provided enormous thermal mass, a conical above-ground dome, wind catchers on the roof to direct air downward, and an underground reservoir to store ice harvested in winter. The thermodynamics of that structure are identical to the combination of methods described in this video: thermal mass to buffer temperature swings, night ventilation through the wind catchers, evaporative cooling from the ice surface, and shading provided by the thick dome. Medieval Islamic architecture across North Africa and the Middle East used a device called the malkaf, or wind catcher, a vertical shaft that rose above the roof line to catch prevailing breezes and direct them down into interior spaces, sometimes passing them over water pools or wet cloth surfaces inside the shaft before releasing the cooled air into the rooms below. This is a wind-powered swamp cooler built into the architecture itself, and it needed no electricity, no refrigerant, and no maintenance beyond keeping the wet surface moist. The white-painted buildings of Santorini in Greece and the whitewashed villages of Morocco are not just aesthetic choices, they are thermodynamic ones, where generations of inhabitants learned empirically that white exterior surfaces stayed cooler, making the interior livable through Mediterranean summers without any mechanical intervention. And now, centuries later, UCLA researchers, MIT D-Lab engineers, the U.S. energy sector, and the Environmental Protection Agency are all independently publishing research that validates every single one of these approaches, using computational fluid dynamics, field trials in Mali and Rwanda, satellite temperature mapping, and controlled residential experiments. Testing an IoT-enabled earthen cooling system in a residential setting in Bhubaneswar suggests a maximum indoor temperature reduction to 24 degrees Celsius, while consuming 72% less energy than traditional desert air coolers. And this research highlights the potential of combining traditional earthen materials with modern technology to create a sustainable and energy-efficient solution for indoor air cooling. Earthen vessels utilize evaporative cooling to lower the temperature of water several degrees below the surrounding environment, providing more effective hydration and supporting the body's cooling processes, which makes clay pots an ideal solution for mitigating heat stress, especially in areas where refrigeration access is limited. And by incorporating earthen pots into daily routines, these low-tech, low-cost cooling solutions can significantly enhance safety and productivity during hot weather. What is happening right now in research laboratories and in rural villages simultaneously is a global rediscovery of the same fundamental physics, which is that water evaporation, surface reflectance, thermal mass, and deliberate ventilation are not primitive workarounds for the absence of technology. They are technologies, real ones, governed by real laws of thermodynamics, and the Industrial Revolution temporarily replaced them with machines that consume enormous amounts of energy to accomplish roughly the same result that a wet clay pot and a breeze were already achieving for free. Now here is something even the well-informed person rarely connects. These methods do not just compete with air conditioning. They make air conditioning itself more efficient and cheaper to run when you do use it. If your roof reflects 60% more solar radiation than a dark roof, your air conditioner compressor has to work significantly less to maintain the same indoor temperature, and your electricity bill reflects that directly. A French Leclerc mall turned its 5,030 square meter roof into a cool roof, and the roof temperature decreased from 36 to 22 degrees Celsius on average, with an estimated 27% reduction of air conditioning and electric consumption. This means that even for people who do have air conditioning, applying even one of the passive, reflective, or shading methods described here translates into real financial savings on every single electricity bill from summer through to the end of the year. Increasing the roof solar reflectance reduces cooling loads by 18 to 93%, and peak cooling demand in air-conditioned buildings by 11 to 27%. The range is wide because it depends on your climate, your existing insulation, and how dark your current roof is. But even in the most conservative scenario, a few liters of white paint on your roof is reducing your air conditioning costs by close to 1/5. Now let us be precise about limitations, because the last thing this video wants to do is oversell and leave you frustrated if your situation is different. Swamp coolers and evaporative coolers only work well in hot, dry environments. Evaporative swamp cooling works better with dry air, and if you do not live in a dry climate, a swamp cooler may not be effective, but a dehumidifier not only increases the effectiveness of your swamp cooler, dry air also feels less hot or cold, making it easier to tolerate the heat. For people in tropical or coastal humid climates, the most effective approaches shift toward the reflective roof and window shading strategies, the thermal mass night flushing approach, eliminating internal heat sources, and focusing on moving air across the body rather than trying to cool the ambient air temperature, since even a modest breeze felt against skin drop's perceived temperature by several degrees without any change in actual air temperature at all. Ceiling fan optimization involves running the fan counterclockwise in summer to push air down, creating a wind chill effect that makes the room feel several degrees cooler even without changing the thermometer reading. And the body awareness dimension of this is worth taking seriously, because the difference between core temperature and perceived temperature is real and it matters to your health and your well-being. Cold showers, ice packs on pulse points like wrists, neck, and temples, and frozen water bottles against your skin provide immediate physiological relief by accelerating heat loss from the body's most efficient heat exchange points. Your wrists and neck are points where blood vessels run close to the surface, and cooling them with even a small amount of ice in a cloth rapidly lowers the temperature of the blood circulating back to your core, which is why this has been a standard technique in sports medicine, military heat management, and emergency medicine for decades. Siesta culture in hot climate countries exists because working midday heat genuinely endangers people, and people in those cultures also dress differently using loose, light-colored, breathable fabrics and full coverage, which may sound backward until you understand that fabric against skin wicks sweat and creates evaporative cooling across a larger surface area than bare skin sitting in direct sun. And sleeping low during extreme heat is not just old wives' advice either. Using light-colored bedding and sleeping low where heat rises, or setting a mattress on the floor, are practical interventions that genuinely reduce the temperature at the level where your body is located during the most vulnerable hours of the night. Heat rises, and the difference between the temperature at ceiling height and floor height in a room during a heat wave can be 4 to 6 degrees Celsius, meaning simply moving your sleeping position from a bed to a floor mat can provide as much temperature relief as a small personal fan. Now let us bring all 6 of these strategies into a clear, practical daily sequence that chains them together in the exact order they should be applied, because the sequence matters almost as much as the methods themselves. Before the sun rises, while outdoor air is still cool, open every window and door to flush your home with cool air and charge the thermal mass of your walls and floors with the coolest possible baseline temperature. Around 30 minutes before sunrise, or at the moment you sense the outside air beginning to warm past the indoor temperature, close every window and draw every cover over west and south-facing glass surfaces to lock in the coolness you have accumulated overnight. During the peak heat hours, typically from 11 a.m. to 4 p.m., use your evaporative setup inside the sealed room. Whether a frozen bottle and damp cloth in front of a fan, a bucket swamp cooler, or a Zir pot in the corner to maintain the coolest possible air in your immediate breathing zone. Apply cold packs to your wrists and neck if the heat is intense. Keep your lighting on LED only. Do not cook indoors if possible, and keep all unnecessary electronics and appliances off, since every watt of heat they generate is competing directly against all the passive cooling you have built. In the late afternoon, monitor the outdoor temperature, and the moment it drops below your indoor temperature, begin reopening windows starting from the north or shaded side to begin the cross ventilation cycle that will flush out the accumulated heat from the day. By the time you sleep, your room should be approaching outdoor nighttime temperature, or below it, your thermal mass is again being charged with cool air. And the entire cycle resets for the following day at 0 additional cost. These simple techniques can greatly lower your home's temperature and energy bills when applied consistently.